In this video, we're going to be solving a problem that appeared as problem 6 on the USAJMO, and this problem actually stumped quite literally everyone. No one got points on it, and no one solved the question. To give it more context for how brutal this problem is, let's take a look at the statistics. So as you see here, this is the JMO 2024, and the maximum score was a 36. And you might be wondering, why was it not a 42 with 7 points on each question? Well, that person who got a 36 solved all of 1 through 5, but only got 1 point on problem number 6. All other 252 contestants got 0 points, with no one scoring more than that. So, what is this question that swept everyone? Well, let's take a look at it now. Now, what is this problem that actually stumped everyone? Well, it's shown over here. Point D is selected inside acute triangle ABC, such that angle DAC is equal to angle ACB, and angle BDC is equal to 90 degrees plus angle BAC. Point E is chosen on ray BD, such that AE equals EC. Let M be the midpoint of BC. Show that line AB is tangent to the circumcircle of triangle BEM. So I'm gonna go ahead and give the best motivation for the cleanest solution that I could find, and give the motivation as best as possible. So let's get started. So this is a geometry problem. So the first natural thing to do, as we should with all geometry problems, is to draw a diagram. So in this case, we have our triangle A, B, C, which is acute, and then point D selected inside the triangle, so that angle DAC is ACB. So it's something like that. And angle BDC is 90 degrees plus angle BAC. So we're looking at something around here. And point E is selected on ray BD such that AE equals EC. So we can expect E to be around here. So, and M is the midpoint of BC. And we wish to show that BEM is tangent to AB. So we have this perpendicular bisector of AC thrown in because that's how we naturally interpret EA is equal to EC. So we might want to restate the problem with B being on the top such that this perpendicular bisector is vertical. So let's go ahead and clear this diagram and make a new one. So we now have our new diagram, but instead B is on the top. And then we put A and C here. Then point D is selected such that AD is equal to DC. So D lies on something like that line. And we have point E, we have angle BDC is 90 degrees plus angle BAC. So D could be somewhere around here. Point E is selected on ray BD such that AE is equal to EC. So this is point E. And now the perpendicular bisector is vertical. And if we let M be the midpoint, we wish to show that BEM is tangent to ABC. No, AB, sorry. So something is suspicious about this midpoint here, because this midpoint, it just randomly got thrown in. So this motivates us to take a homothety of scale 2 at point B, because that will get rid of this midpoint from the problem. And we're not taking the homothety of point C because the lines don't seem to pass through that point at all. So without further ado, let's take the homothety. So then M gets mapped to point C, then point B is fixed, and then point E goes somewhere over here. And we want to show that this circle here is tangent. So how do we interpret the perpendicular bisector condition, AE equals EC? Well, we can draw the foot of the altitude. That's what happens if we take a homothety of scale 0, so to say, which means that we have B as a foot onto AC. Then the foot of E onto AC is just a midpoint. So when we take a homothety of scale 2, we'll just get the reflection of the angle of the foot of the altitude across the midpoint. So thus, E prime, the image under homothety, lies under something like that. and we also have this line here. And we're extending these lines because we don't know what we can do with them. So we might think that this intersection here is useful. So let's label it B prime. Now, what is this point B prime? Well, look at this. Note that B and E are the perpendiculars from B and E prime are reflections across the midpoint. So that means that B and B prime the lines perpendicular to AC going through B and B prime are reflections across the angle, but no, the perpendicular bisector, sorry. And moreover, since angle CAD is equal to angle BCA, that this means that this triangle here is isosceles and it intersects at a point such that AB B prime C is an isosceles trapezoid. So it definitely appears that this point B prime will be useful. Let's see what we can do. We now go back to the main problem in hand. We want to show that AB is tangent to the circumcircle of triangle BE prime C. So given this, we might want to use a tangency condition. So we wish to show that directed angle ABC is equal to directed angle BE prime C. And we're hoping that this will turn out nice somehow. And let's go ahead and so we also know that B lies on line DE prime. So this is, we want to prove that these are equal. So this is directed angle DE prime C. And we want to show that this is ABC. But now we have this point B prime here that we haven't used. And moreover, B prime lies on the circumcircle of ABC, which is incredibly useful. So we might want to use that somehow. So how can we use it? Well, the fact that B prime lies on AD will come into play now. So ABC, because B prime lies on the circumcircle, it is equal to directed angle AB prime C, and that is equal, and in turn, that is equal to directed angle DB prime C. Now look here. We want these two to be equal, and look, we now reduce the problem to showing that DB prime E prime C is cyclic. If we could show this, then we'd be done. So how do we actually go about showing this? At this point, as with all geometry problems, whenever we haven't used a piece of information, we should probably use it at some point. In this case, the information that we haven't used yet is that angle BDC is equal to 90 degrees plus angle BAC. We use this condition here because we constructed the isosceles trapezoid in that way. And we use this condition here so that E prime B prime would be perpendicular to AC. So we haven't used the fact that angle BDC is equal to 90 degrees plus angle BAC. So let's try using this to prove our quadrilateral is cyclic. So how can we relate it to our cyclic quadrilateral? Well, this is also because BD and E prime are collinear. BDC plus CDE prime is 180 degrees in normal angles. So directed angle CDE prime is equal to 90 degrees minus angle BAC. And hence, to prove that the quadrilateral is cyclic, we must show that this angle here is 90 degrees minus angle BAC. And because of our right triangle that we produce here, the right angle, because B prime E prime is perpendicular to AC, we want to try using something like that, and that reduces down to proving that this is equal to angle BAC. But now we recall that ABB prime C is an isosceles trapezoid, and therefore these two angles are equal since they're the two base angles of an isosceles trapezoid. And alright, so that was kind of fast. So how exactly do we solve the problem? So I'm going to go ahead and restate the motivation for the problem and its solution. So we have this random midpoint here, and we're inspired to take a homothety centered at B. So that brings the point E prime, no, E to the point E prime here. And we want to prove that BE prime C is tangent to AC. Then the condition EA is equal to EC equates to the perpendicular from E prime to AC being the reflection of the perpendicular from B to AC across the perpendicular bisector of AC. And we also have the line AD here, which can be naturally interpreted as these two base angles being equal, and so they intersect at this point B prime such that AB B prime C is an isosceles trapezoid. Then, in an effort to try doing something, we ended up reducing the problem to proving that D B prime E prime C is cyclic. And we finally went back to the condition here and used that to prove that this was indeed true, which indeed solved the problem. So thank you so much for watching this video. Please subscribe if you'd like to see more.